The aim of this lecture is to describe the main characteristics of the radioactive decay, starting from its experimental evidence. We all know very well that nature is made of atoms, tiny bricks of matter constituted by dynamic particles, electrons, that rapidly move, in some ways, around a massive static nucleus made by protons and neutrons, also called nucleons. The number of protons defines the atomic number Z, while the number of protons and neutrons define the mass number A. Nuclei having same atomic number Z but different mass number A are called isotopes. At the end of the 19th century, the French scientist Henri Becquerel discovered that some nuclei have the tendency to spontaneously transform into other nuclei by emitting particles, called radiation. If we take a piece of rock and place it in contact with an instrument able to emit a sound signal when hit by particles, the final effect is this. Can you hear it? Okay, at present we do not know exactly what it is, but we all realize that there are fast pulses, the radiation, randomly distributed in time. This is the first fundamental property of radioactivity, randomness. It is interesting to note that, although random, the radiation emission typically varies in time with a velocity that strongly depends on the sample composition. By considering the mean trend, the experimental evidence shows a global time evolution correctly modeled by an exponential decay law, with a constant exponent, lambda, that takes the name of decay constant. As a result, the decay always maintains the same speed as a process that does not age. More mathematically, there is an evidence each nucleus within the sample has a constant probability lambda of decaying over time. The value of lambda is characteristic of each nucleus. The unit of measurement of the decay constant is the inverse of a time, typically 1/second. Instead of lambda, it is often convenient to define, from an operational point of view, the half-life, the time required for the number of radioactive nuclei present at the initial instant to be halved. Let's go back to lambda. Being it the probability of decaying of a single nucleus, the product of lambda by the number of nuclei present at time t, nt, gives the total number of decays per unit time, called activity. Activity is measured in becquerel, which corresponds to 1 decay per second. 1 gram of radium, for example, has an activity of 3.7 10 to the 10th becquerel. Therefore, it emits 3.7 10 to the 10 particles per second. This is not just any example. It refers to another unit used for the activity, called Curie, not belonging to the International System of Units, but still used in some context. What happens to a nucleus after the decay? The best answer is it depends. It depends on the type of decay. We will see the specific properties of the different possible processes that actually occur in the next video. What we can say at present is just what happens in time to the products of the decay, the daughter nuclei. Let us first consider, for simplicity, a sample of radioactive nuclei N1 which transform through a unique type of process into stable nuclei N2, by starting from an initial condition where only N0 nuclei of type 1 are present. Daughter nuclei N2 will grow exponentially from 0 to N0, with a rapidity governed by lambda. Of course, this refers to a simple and quite rare case. In real life, a radioactive nucleus can generally decay in different ways. For example, guess that type 1 nuclei can decay to daughter nuclei of type A and B. Conditions A and B can in general refer to different type of nuclei or to different conditions of nuclei of the same type. The total decay rate, lambda total, can be expressed as the sum of a partial decay rate, lambda A, associated to the way A, and the partial decay rate, lambda B, associated to the way B. The parent nuclei of type 1 will decay according to the exponential law already described before, the same its activity. Daughter nuclei, N2A and N2B, on the other hand, will follow the evolution of N2 seen before, properly weighted by the ratio of lambda A or lambda B and lambda total, the so-called branching. Another common situation is a radioactive nucleus that decays into product nuclei which are in turn radioactive, giving rise to the so-called radioactive decay chain, in which there are transitions from type 1 to type 2, 3, 4, etc. Each species of the ITH generation is fed by the decay of that of the previous generation and decreases due to its own decay. The mathematical description of this situation requires the use of differential equations which describe the instantaneous balance between the production of nuclei given by the parent nucleus and the decay itself. The solution of the system of equations is given by the so-called Bateman equations. So far, we focused on the experimental evidence and related statistics of a nuclear process which led to the emission of particles, called radioactivity. A growing knowledge of such a peculiar and complex phenomenon allowed to understand that the emitted particles are not of the same type and that very different processes are actually involved in radioactive decays. Nevertheless, despite the physical differences, a common aspect can be highlighted. All spontaneous transitions involved the emission of energy. Therefore, all transitions occur for reducing the energy content of the nuclear system. Transformations are associated to an internal instability that the nucleus tries to recover. What is the origin of this instability? Why nuclei decay? Lots of factors affect the energy conditions of a nucleus. Forces between nucleons and inside nucleons, nucleus distribution and dynamics, final nuclear shape and dynamics, etc. The final effect is generally represented by an energy level at which a nucleus lays, level that is called ground state or excited state when it refers to the minimum energy level allowed for that nucleus or not, respectively. To conclude, during this lecture we saw that some nuclei have the tendency to spontaneously transform into other nuclei with a time evolution described by an exponential decay law which depends on the decay constant lambda. Radioactive nuclei can generally decay in different ways and into different product nuclei which may be radioactive themselves. These spontaneous transformations are due to a reduction of the energy content of the nuclear system.